This is the screencast for section 3.2, example 3. Again, we're working with exponential growth and decay models. We're going to model some bacteria growth now in a more specific circumstances. Suppose a culture of 100 bacteria is put into a petri dish and the culture doubles every hour. So doubling means that next hour I'm going to have 200% of what I have now. The original 100% and another 100%. 200% of what I have now. Predict when the number of bacteria will be 350,000. So P of T, our population, equals the initial value, initial population was 100 bacteria. Next hour, I'm going to have 100% of what I have now plus another 100%. And that happens every hour. So my exponential growth function is 100 times 2 to the t. There's my 200% that I was talking about. 200% next hour. 100% of what I have now plus a new 100%. It's doubling. So the question is, when will the bacteria be 350,000? So I'm going to put 350,000 in for my desired population value. And I'm going to solve using my calculator. So in y1, I put my exponential growth function that I just came up with. Then in y2, I put 350,000. So my y max for my window is going to be pretty easy. 350,000, I can bump that up to maybe 400,000 or even 500,000. The question is, how long is it going to take this bacteria to go from 100 to 350,000? How many hours? If it was linear, that'd be easy. That would be 3,500 hours. But this isn't linear, it's exponential. It's going to take way less time than that because it keeps growing faster and faster and faster. So I'm going to take a wild guess and I'm going to say somewhere around 30 hours, but I don't know. I could be way off. I just got to start somewhere. So for my graph, 30 hours was definitely too long, but at least I can see my intersection and find out when the population will reach 350,000. So it'll take about 11.77 hours for 100 bacteria to turn into 350,000 since they are doubling every hour. The now try problem for example 3 is number 15. Same instructions. Determine the exponential function that satisfies the given conditions. So the initial mass is 0.6 grams and that mass is doubling every 3 days. Interesting. Every 3 days. So not every day, but every 3 days. Okay, which means after 1 day, 1/3 of the doubling will have happened. After 2 days, 2/3 of the doubling will have happened. And after 3 days, 3/3 of the whole doubling will have happened. So in my setup, I'm going to say P of T equals my initial mass 0.6 times, now it's doubling, so we've already talked about how that base value is going to be 2. 200% of what I have now is going to be there the next unit of time, which in this case is every 3 days. So now my exponent isn't going to be t, because t means every day. I have to do t over 3. 1 day is 1/3 of day. 1/3 of the doubling. 2 days is 2/3 of the doubling. 3 days is 3/3 of the whole doubling. So 2 will be raised to the first power after 3 days. So here's my exponential function. So to show you how this works, this isn't required by the instructions, but I put my function, my exponential growth function into y1, and then I graph this on my calculator, and I'm going to trace and show you some values. So if we start out with 0.6 grams, after 3 days that should double. So if I put in 3, enter, I should get 1.2 grams, twice of 1.6. After another 3 days, so after 6 days, that will double. So I'll have 2.4 grams. There it is. After another 3 days, that will double. So in 9 days, I should have 4.8 grams, etc.